Okay, it worked.
Okay, so please speak up if that stops showing, because I apparently have no indication on my end. I see now a green. Okay, I think we should be okay. All right, so I'm going to minimize that now. So international safeguards. So as I said, we have, verification is kind of one of the fundamental aspects of nuclear safeguards, and that is verifying that nuclear materials are being used by a country to support a peaceful nuclear program and not to support an illicit weapons program. And so the non-destructive assay measurements that we're going to talk about are part of this verification component of safeguards, which is just, we trust that states are cooperating with their agreements, their non-proliferation treaty agreements or other agreements, and that trust, though, is verified through measurements of their materials. So the objective of safeguards is the timely detection of diversion of material. And so there are two components of this verification. It's to detect that something has gone missing and detect it with some probability or some confidence. And then also to do that within some period of time, within, what we say is a timely manner or timely fashion. Okay, so on the right here, I have the nuclear fuel cycle, just as a reminder. And so you can see that we have natural uranium that's mined. It again goes through milling, conversion, enrichment. At that point, it might be made into nuclear fuel, which would go into a nuclear reactor. After going through the reactor, it would come out as spent fuel, be stored in a pool or in dry cask storage, and then it may go off to disposal, or it could go off to reprocessing. So all aspects of the nuclear fuel cycle are essentially, important to be safeguarded. There's sort of what we call the start of safeguards and the termination of safeguards. So we don't need to be monitoring uranium in the ground necessarily, but there is, the IAEA determines where do we need to implement safeguards within the nuclear fuel cycle in order to accomplish this mission of verifying that the nuclear material is not being taken from a peaceful program to an illicit program. Okay, so the IAEA today, the International Atomic Energy Agency is the body that is responsible for implementing safeguards. So they have a lot on their plate. This infographic I got for 2018 on the right here shows that they have monitoring activities in 183 states. They've got over 200,000 significant quantities of material that they're monitoring, and that's in over 1,300 nuclear facilities. So it's a massive amount of work that has to be done. And they're essentially a volunteer organization. So they receive funding from their member states, but it's all on a voluntary basis. And the reason that states contribute to the IAEA in order for them to accomplish this mission is that there's been global recognition that we are all safer if nuclear material is properly accounted for and properly safeguarded. And so it's in everyone's best interest that we work together to implement safeguards. And that's why, all the member states take part in, with the IAEA in this inspection process through financial donations, through cost-free expertise. They send experts over to the agency. There's all sorts of ways that member states contribute to this mission. And then the IAEA is ultimately responsible for performing this verification. So in addition to, their kind of standard inspection responsibilities, the IAEA today is currently working to achieve universal acceptance of the additional protocol. The additional protocol is kind of an additional set of agreements that a state would make with the IAEA in addition to their comprehensive safeguards agreement that they would have made with the agency, as they signed to the non-proliferation treaty, after they signed that treaty. So the additional protocol is highly regarded by the IAEA and around the world because it provides the IAEA just a bit of additional access and short notice inspections and those sorts of things that really make everyone safer. And so, the IAEA, as you can see on the infographic, as of 2018, had 134 states with the AP in place, and they're working on getting all states to sign on to that. So additionally, safeguards by design and as well as unattended monitoring and data integration are two sort of technical objectives of the IAEA. And the reason for that is, as I said, they have a great deal of inspection work to do on a very small budget. And so the more that they can have safeguards integrated into the design of facilities rather than going to facilities after they're built and saying, how do we implement safeguards here? That makes their job easier in the long run. Same thing with unattended monitoring and data integration. The more inspection work that they can do remotely without having to have someone physically present on site, the better that is for the agency's ability to conduct, more inspections with less resources. So finally, one thing that they're currently have been working on for many years, but are focused on at the moment as well, is implementation of the state level concept. And so the state level concept is essentially assessing each state as a whole and using all available safeguards indicators. So that's open source data. That's the data that comes back from when inspectors go to a facility. That's essentially anything that they have that supports their safeguards conclusions and integrating all of that information to draw more comprehensive conclusions and do so in a way that addresses the state as a whole. So additionally, they're working on deciding upon a consistent and unbiased strategy to implementing or developing these state level approaches within each state. And so, a few of the changes from sort of what I'll call traditional safeguards and the state level approach to safeguards are that, under traditional safeguards, the IAEA looks at facilities, individual facilities, and the materials within those facilities and assesses the attractiveness of the materials and then implements safeguards according to that. Under the state level concept, there's more examination of all acquisition paths that exist within a state. So they're looking at the attractiveness of the acquisition paths as opposed to just the attractiveness of material in individual facilities. So it's a whole different kind of way of looking at a state and their nuclear facility. And then the really important thing is that it also, this different way of looking at the state determines how the agency will apply their safeguards resources and distribute their safeguards resources. So, so that's another very relevant topic at the IAEA right now. Okay, so now we're going to sort of dive into non-destructive assay, starting with special nuclear materials. So I think I've tossed that term out once or twice already, but special nuclear material is with, in the US vernacular, it's nuclear materials that can be used to make a weapon. And so that's, for our purposes, highly enriched uranium and weapons-grade plutonium. So highly enriched uranium is found on the front end of the fuel cycle. We talked about, uranium is mined from the ground, then it goes through milling, conversion, and then enrichment. So, so we need to monitor the enrichment plants or, front end of the fuel cycle to monitor HEU. On the back end of the fuel cycle, after fuel comes out of a nuclear reactor, it contains plutonium. And so we need to monitor spent fuel and reprocessing facilities in order to monitor the plutonium. So in non-destructive assay is the most commonly employed technique for material accountancy. This is for a few reasons, but essentially, if you want to know what's in some chunk of material, you have to either take a piece off, dissolve it in some way, and do some kind of chemical analysis on it, maybe mass spectroscopy or something similar. Or you need to, measure it in the form it's in, measure some characteristic of it, some physical characteristic of it. And so that's what NDA is. It's not destroying an object at all, just measuring the characteristics of the item as it exists. And in particular, NDA uses neutron, it measures the radiation that comes out of some sample or some material and uses that to characterize it. So non-destructive assay instruments typically consist of a series of gamma or neutron detectors, or it could be a calorimeter to measure the heat. And so basically, we're just measuring the radiation that comes out to determine things like, the quantity or material of the sample. And the parameters of the radiation, we might measure the energy of the radiation emitted, we might measure the timing, the intensity, or realistically, in most cases, all of those to determine, what is in the sample that we're measuring. So you can break NDA in neutron and gammas. You can break it into essentially two categories. You can break it into passive, which is where there's just a sample, there's a detector, and we're measuring what's coming out, or maybe a series of detectors. Or there's active NDA, where you have your sample, and then you have some interrogating source, maybe neutrons or gammas. You induce fission, or you induce some signal within the sample, and then measure that induced signal. So that's why it's active interrogation, because you're actively inducing a signal that you're measuring. So the type of special nuclear material that you're measuring with NDA will dictate or determine what type of non-destructive assay you should implement, passive or active. So for example, plutonium is a strong passive neutron emitter. It emits plenty of neutrons all on its own because it tends to have a strong spontaneous fission isotope, which is plutonium-240. Uranium, on the other hand, does not passively emit a lot of neutrons. If you have a neutron detector and you put a piece of uranium next to it, you may measure almost nothing above background. And that's just because uranium-238 is your primary spontaneous fission neutron emitter within uranium, and it's just a very, very, very weak passive signal. So if you wanted to measure the neutrons from uranium, you would need to induce, use some active NDA to induce more signal to be measured. So diving a little further into the difference between neutrons and photons. And again, I like to point all this out because I think that those who are familiar with radiation detection tend to be much more familiar with the gamma ray side or the photon side than the neutron side. Whereas, like I said, I focus on the neutron. So I like to talk about both and make sure, that we differentiate between the two, because they're really two very different problems whether you're measuring neutrons or photons for NDA. So first of all, there are different, sources of origination of the two particle types from special nuclear material. With neutrons, we see the neutrons emitted, almost exclusively from spontaneous and induced fission or alpha N reactions, where an alpha particle interacts with a low Z isotope and produces a neutron, a single neutron. There are other sources of neutrons, but they're very, very uncommon. With gamma rays, on the other hand, or photons, we see gamma rays that come from the nucleus, we see, or nuclear collisions, and then we see X-rays that come from the electron cloud. There are gammas that come from fission as well, but typically when we're characterizing we're characterizing special nuclear material with non-destructive assay, we're focused on gammas and X-rays that come from these locations, from the nucleus, nuclear collisions, or electron clouds. And then this next piece is really crucial for NDA. So the signal that we are interested in from neutrons is different, typically, than the signal we're interested in from photons. So for neutrons, what we're typically measuring and interested in is time of arrival or time of detection and correlations. With photons, we're interested in energy. So this is an interesting distinction because, again, if you're familiar with radiation detection and with photon gamma ray detection in particular, you're used to seeing how many gamma rays were detected of X energy. So you're looking at intensity and energy, and that's because those parameters tell you, what isotope is emitting that gamma ray, and you can use that to determine the quantity. With neutrons, the neutrons that are coming from fission, they come essentially all in the same energy spectrum, the Watt spectrum. And so you can't really use the energy to differentiate between isotope, emitting isotope like you can with gamma rays. So it just requires a different way of looking at things. If you're used to gamma rays, then you have to shift your mindset for neutrons to think about time and correlations instead of energy, much of the time. There are always exceptions, but most of the time. Okay, on to shielding. As you probably know, there are different shielding materials that you're going to use for photons and neutrons. With neutrons, we use low Z material, such as high-density polyethylene or water. With photons, we're going to use high Z material, such as lead. And then finally, the detectors. So a lot of non-destructive assay systems for neutrons they utilize helium-3 detectors. That's a thermal neutron detector. There's also fission chambers, which is also technically a thermal neutron detector, but much lower efficiency, and then scintillators. And on the photon side, you can see scintillators again. So that's actually a dual particle detector, which comes with lots of advantages and also lots of challenges. We could give a whole nother talk just on scintillators and how, how they apply to NDA. So another common detector for photons, especially if you need good energy resolution, would be high purity germanium. A bit lower resolution detector, sodium iodide. Okay, on to neutrons. So a brief history of neutron counting. Back in the day when there was not nearly as fast of pulse processing electronics, we did total neutron counting, meaning we just recorded the total number of neutrons that were detected in some amount of time. Using this method, you can determine some quantities or some characteristics, I should say, of some nuclear materials, but it's not going to be all that accurate, and you're really limited to the types of materials you can look at. So as pulse processing electronics and other parameters of detectors, materials and so on improved over time, we moved on to coincidence counting. And coincidence counting is where we're recording the number of times that we get two neutrons within some set time window that we call a gate. So we're looking for pairs of neutrons in coincidence counting. And the reason for that is that pairs of neutrons can typically be associated with fission events. And so this has a really wide application for international safeguards. Coincidence counting is still the neutron counting method of choice for identifying, characterizing the special nuclear material in a lot of applications. And then finally, again, pulse processing electronics got faster, data storage got better, so on and so forth. And this was extended to neutron multiplicity counting. So if you're following the logic here, total neutron counting was looking for single neutrons or total number of neutrons over time. Coincidence counting is looking for pairs of neutrons, or how often do we get two neutrons within some time window. And then multiplicity counting is just the natural extension of that. So how many times do we get 3 neutrons within some time window? How many times do we get 4 neutrons, 5 neutrons, and so on? So this improves our accuracy of our neutron assay by quite a bit because you're adding so much more information. However, there's a drawback, which is that your efficiency of detecting total neutrons goes as, it's proportional to the efficiency of the detector system. The efficiency of detecting coincident neutrons goes as is proportional to the efficiency of your system squared. And so consequently, the efficiency of detecting 3 neutrons in some time window is proportional to the efficiency of your detector system cubed. And so you can imagine that this problem gets really hard really fast. The more that you're looking for, if you're looking for, triplets or, 4 neutrons, 5 neutrons within some time window, then your efficiency problem really starts to come into play. So there are applications that are really well suited for neutron multiplicity counting, but as a result of this efficiency challenge, coincidence counting is still much more widely used, more popular method. So here is just an example of kind of what a passive neutron counter, coincidence counter might look like. So you might have some fissioning source or some sample that goes in the middle of a ring of detectors, and you're looking for emission of, or detection really, of those prompt neutrons that came from fission. And then you're going to use that information, the coincident information or the multiplicity information from a multiplicity counter to calculate the mass of the isotope that is fissioning. Okay, so I'd like to do a bit of a deep dive here into neutron coincidence counting, kind of what is the theory behind it and why does it work and how does it work? So for this, I like to do a little thought experiment. So imagine that there is a spontaneous fission event. And from this spontaneous fission event, there are 3 neutrons emitted. So the first neutron thermalizes in, whatever moderating material is in your detector system and is detected at some point in time. The next neutron takes a little bit longer to thermalize, but then it's also detected. And then the third neutron causes another fission event within the material. Okay, so then that fission event emits 2 neutrons. One of them escapes, one of them causes another fission. This time 2 escape, 1 is detected. So now we have another pulse in time here. And this goes on and on and on until all the neutrons from this fission chain are either detected or escape. So all these neutrons that you see here on this time axis are correlated. And that's because they all came from the same fission chain. So correlated neutrons in our vernacular come from the same fission chain or the same fission event. So basically, this concept, the fact that these neutrons are all correlated is a fundamental theory behind neutron coincidence counting. We're trying to detect, all these correlated neutrons. But how do we know that neutrons that we detect in our system, how do we know whether they're correlated from the same fission chain or same fission event, or uncorrelated or accidental coincidences? Because this is never what we actually see, right? We never see a single fission chain happening within some material. What we actually see is something like this times 1,000 or 100,000 or 1,000,000. There's all these overlapping fission chains that are all happening at the same time, emitting neutrons, and all these neutrons are being detected in time. So how can we tell? I'm going to try to annotate here. Sometimes this goes well and sometimes it doesn't. So how do we know, for example, that these neutrons, which are detected really close to this neutron, but how do we know that those are not from the same fission event or chain? Because this neutron came from that one, and these neutrons came from a totally unrelated fission chain. And so the answer to that is basically statistics. We measure for some amount of time, and then we can start to say what portion of the neutrons came from the same fission event or same fission chain, and what portion of the neutrons came from totally unrelated fission chains. So I'm gonna, see, this is where annotating always catches me. I have to stop annotating. Uh-oh, I stopped sharing. Okay, we'll get there. Okay. There we go. So a Rossi alpha distribution. This to me is the most reasonable way to understand how we determine whether neutrons came from the same fission event or the same fission chain or from a totally unrelated fission chain. So this basically goes back to the geometry of your detector system. So consider a single fission event. Consider that within that fission event, 1 neutron went out and was detected. And the second neutron went out and had a whole bunch of scatters within your moderating material, and then was detected some amount of time later. So there's a finite amount of time between those 2 detection events. And same thing for a single fission chain. There's only so long that a fission chain, realistically can propagate in some material. There's only so long that can elapse between the detection of neutrons within that fission chain. And so what we do is, by looking at this Rossi alpha distribution, the x-axis here is labeled here time, but it's actually time between neutron detections. So we say that some neutron detection happened at time 0, and then some second neutron detection happened at some other time, and that's what is marked on this distribution. That's what creates this histogram. Okay, so we're saying that there's only so much time that can elapse between 2 correlated neutron detections. And so what we do is we set up this time gate, the A time gate. I'm going to annotate again at my own peril. This time gate, which we set up so far out in time that there's just no way that neutrons detected here could have been correlated. They could have come from the same fission event or the same fission chain as the neutron detected at time 0. So, this is an abbreviated axis here, but really this time is very, very long. This D we call the long delay, and it's about 1,000 microseconds or a little longer. And so, what we say, again, to reemphasize, is that there's no way that two neutrons that were emitted from the same fission event or the same fission chain could have been detected, you know, out here and at time 0. And so we set up this accidentals gate. So we say all the neutrons that are detected at this time are uncorrelated to our trigger neutron or our time 0 neutron. And therefore we have kind of our background, you know, our accidentals background basically. And then we can subtract that from this region to get our correlated neutrons. And so this is the easiest equation in all of science. We have this R plus A region here, which is, please forgive the terrible writing, which is our, you know, our region here. That's our, we call it our time gate, but it's the, you know, the gate that we open in our shift register to detect neutrons that are correlated. And then we subtract off this A gate, which is so far out in time that the neutrons can't possibly be correlated to the trigger neutron. And that gives us R, or our coincident neutrons, our true coincident neutrons that came from the same fission event or same fission chain. So that's neutron coincidence counting in a nutshell. I'm gonna try to stop annotating, haha, okay. And with that, oh no, the annotating keeps, okay, hold on, let's see here. We can clear all drawings. All right. So that's how neutron coincidence counting works. That's how we detect our correlated neutrons from the same fission event or same fission chain. And that's ultimately how we take that real number, that correlated neutron count rate, and we can trace that back to some quantity of fissionable or, you know, material, special nuclear material that we're trying to determine. Okay, so this is an example of a multiplicity counter. So as I mentioned, a multiplicity counter has to have very high efficiency. So 65% is pretty darn high for a non-destructive assay instrument. We have 121 helium-3 tubes in this system, and the die-away time is 22 microseconds, and that's essentially just a parameter capturing how long neutrons can live in this system. You use that parameter to determine that gate width that I just mentioned, but that's probably beside the point. So this system, again, an example of a multiplicity counter, coincidence counters can be considerably smaller than this. They don't need to have nearly as high of efficiency, but if you want those triples or quads or pents, then you have to have a really, really high efficiency system such as the ENMC here. Okay, so that concludes the neutron portion of the non-destructive assay overview. I'm going to move on to photons now. So for photons, we use this generic assay equation, and an emphasis on generic here, because this is, you know, this applies to pretty much anything. But the idea is that your mass of special nuclear material is proportional to your measured radiation rate, or, you know, intensity. So how many gamma rays do you detect per unit time in some energy bin? And then that value is corrected for things like self-absorption within your material, container absorption in whatever is holding your special nuclear material, and then your measurement system electronics, which may be sensitive to things like, you know, dead time. So the reason for this, so gammas are a lot more subject to interference from the materials within the container, or even the material itself that's emitting the gamma rays, because as we said, gammas are shielded by high Z material. And what is uranium and plutonium if not high Z material? So, so these items are what we call self-shielding. The special nuclear material is self-shielding when it comes to gamma rays. So, you know, that means you're only detecting gamma rays really from the very outer few centimeters at best of your item that you're measuring. Additionally, a lot of these, you know, materials might be contained in some sort of stainless steel or lead or tungsten container. In that case, you're also going to have absorption within the walls of the container holding your material. So these have to be accounted for because they're going to reduce your detection rate. And then finally, there may be some calibration constant that you're correcting for to determine your special nuclear material. And that calibration constant will usually be determined by using, you know, a variety of samples that are all similar in size and in type to whatever it is you're measuring. So MGA is multi-group analysis, And this is analysis of, the low energy X-ray region as well as the gamma ray region that you use this analysis type to determine plutonium isotopics. And that's just because there are some characteristic gamma rays that are emitted from plutonium in this energy region. So when you have a high resolution detector, such as a high purity germanium, then you can differentiate between these gamma ray energies and the peaks in order to determine the relative peak intensities and therefore the relative contributions of different isotopes of plutonium. And so I love this image because to me, this exactly shows a couple of things. One, why you really can't do this on your own. It's very hard to disentangle all of the different contributions that contribute to your measured signal, which is that white dotted curve up there. So you have all these different additive gamma rays that form all these peaks. They give you all these peaks in different energies. They all add together to make the signal you're getting with your detector. And then this MGA software, this analysis algorithm, can go back and decouple and disentangle this signal to show you what are the contributions from individual isotopes. And then it pops out this nice report, which shows you what's the relative abundance of the different isotopes of interest. Additionally, the same sort of analysis method applies to uranium. We call it MGAO, or just multi-group analysis for uranium, very simple. And so again, this uses a low energy region where you have some very characteristic gamma rays. And again, you have these overlapping peaks that are attributed to different isotopes of uranium, as you see here. And then your MGAO can go ahead and show you what are the different contributions from the different isotopes. So, when I talked about neutron NDA, you're really only getting quantities of, fissioning material. So you might get quantity of plutonium-240 from the coincidence counting methods from neutron counters. So you really have to couple with a gamma technique such as MGA to get your different isotopic contributions. And oftentimes that is what we're interested in NDA. We're not just interested in elemental plutonium or plutonium-240, but we want to know how much plutonium-239 is there, how much fissile material is there. And so to do that, you really do need to be able to apply a gamma method. And so neutron and gamma methods go very well together. The best case scenario is applying both measurement techniques, a gamma and a neutron technique, to get all the information that you need about some sample you're measuring. All right, heat, I'm doing pretty well on time here. So the last one I'm going to talk about just briefly is heat. And calorimetry is the standard method for heat measurement, non-destructive assay. This is a very well-established and precise method of NDA, and it uses the thermal power that comes out of radioactive decay or fission to determine the mass of special nuclear material. So heat flow calorimetry gives you a very precise answer of your material, whereas NDA, neutron and gamma-based NDA typically come with uncertainties that can be decently high. But the reason that calorimetry isn't just then used universally, because it gives us a more accurate answer, why wouldn't we just use it all the time, is that it takes a very, very long time. So you have to let an item reach thermal equilibrium. It can be, it can be basically prohibitive to whatever inspection process you have to wait long enough or do a long enough measurement to complete calorimetry. And additionally, there are items, that can't actually fit in a calorimeter. So that is another challenge. However, calorimetry is a very reliable NDA method. It's used quite a bit at LANL for our own material accountancy work. And so, it's worth discussing here. But yeah, it takes quite a bit longer. So for, IEEA inspection purposes, for much of the time, it's not going to be applicable. Okay, so with that, I just wanted to share this slide of, safeguards at LANL. We've been supporting the IEEA through training. Every IEEA inspector has come to Los Alamos for training since the 1980s. We've been supporting through non-destructive assay technology development. Essentially, every neutron-based NDA system used by the IEEA came out of Los Alamos. We support them through cost-free expertise. We support them through development of analysis algorithms. So we've been playing in the safeguards field and supporting the IAEA in this very important mission for well over 50 years now. I think we're up to about 54, 55. This was a few years ago that we celebrated our 50th anniversary. And so hopefully that gave you a good introduction to a non-destructive assay. As I said, tomorrow we'll focus on NDA specifically for spent fuel. So with that, I'm happy to take any questions. I can't tell if any have come through yet, but I'll leave my slides up in case we want to go back and look at anything.
Awesome, thanks, Alexis. Question from Braden is, what is the use of knowing if neutrons are correlated with each other?
I'm gonna have to repeat that one more time.
Sure. The question is, what is the use of knowing if neutrons are correlated with each other?
Sure. So if you think about what we're trying to determine, right? We want to know how much, for example, how much plutonium-240 is in some sample. Plutonium-240 is fissioning at some known rate. We know, the special activity of plutonium-240, specific activity of plutonium-240. So that's how many times it's decaying, how many fissions per second per gram, right? So we know that quantity. And then if we can determine how many correlated neutrons we're getting, we know correlated neutrons come from fission, because if they're emitted at the same time, they're going to be detected at close together time. And just by the definition of correlated neutrons, as I've talked about, correlated neutrons come from fission. So if we can take, amount of correlations, number of correlations, or rate of correlations, then we can trace that through, a calibration parameter to mass of material. And so if we want to determine the mass of a material, which is why we do NDA measurements, then we can use those correlated neutrons to determine that parameter.
Cool, thanks. A question from Professor Perfetti is, how sensitive is this fission chain discrimination to uncertainty in nuclear data, for example, NUBAR or the Chi spectrum?
I'm sorry, Mike, for some reason, I'm having a hard time understanding. Can I read? Let's see. Can we open the chat and see if I can read? Aha, there we go. Okay. How sensitive is this fission chain discrimination to uncertainty in nuclear data? Good question. So, for what we're looking at here, there's not a lot at play. So we're looking at, plutonium-240 emissions. So really, the nuclear data that is contributing to our taking that correlated neutron amount and tracing it back to some measurable parameter. It's really done, those calibration curves are determined empirically. We've done, thousands of measurements of plutonium. We can take some measured, neutron rate, correlate it to plutonium mass, and there you go. So in this case, in non-destructive assay of straight plutonium, straight uranium, the nuclear data has, I would say, little to no effect. Now, there are a lot of cases, especially spent fuel, which I'm talking about tomorrow, where the nuclear data has a considerable effect on basically our knowledge of the content of the material. And because we don't perfectly know the content of the material from simulations and the nuclear data, then we also can't correlate that to our measured signal correctly. So hopefully that kind of answered your question.
Well, and then I'll try to yell right into my mic. Hopefully it's better. When you say timely fashion for IAEA inspections, what does that really mean? Is that minutes? Is it hours? Does it depend?
Good question. So, before proliferation is the ultimate goal, right? We want to detect it before some material is turned into a weapon. And so that's kind of part of the reason that the IAEA is going back and reevaluating the way that they implement safeguards, in the sense that, as they do this acquisition path analysis, they're looking at, what are the steps that a state may go through to produce a nuclear weapon? And how long do each of these steps take on average? There's some finite amount of time it takes to process material, to, enrich and so on. And so, now a lot of the state level approaches and kind of the state level concepts, they're utilizing more what is the time to the end of the path in order to determine what is their time window in which to detect a diversion, if that makes sense. So they're they're currently reanalyzing that and rethinking the way that they're determining that timely parameter. But that's, yeah, the short and easy answer is before a weapon's made. That's how quick it needs to be done.
Cool. And then right now, like if somebody was to go in and say, is time dominated by the detectors? Is it like electronics? I guess where's the dominant source of time coming from?
Source of time, you mean in like detecting proliferation, or what do you mean?
If I'm an IAEA inspector and I'm going into a facility and measuring material, and it takes me an hour to measure a sample, is that an hour because my detectors are slow, or is it because my electronics are slow?
Oh, I see what you're saying. Okay, so no, I mean let's see here, how to answer this. So the amount of time, our detectors do need to be quick, they need to be efficient. We need to be able to get answers in less than days. Like I said, the calorimeter can be days. The reason for that, though, is not that timely component of safeguards. It's just facilities. So, I mean, these are operating nuclear facilities that are making money, theoretically, a lot of them. They're part of some nuclear power program. And so we can't, I'm saying we as if I'm part of this, but the IAEA cannot go in and just shut down nuclear facilities for days on end in order to accomplish this mission, right? So that's the reason, the driving force behind having, efficient and reliable NDA measurements. The timescale we're talking about on proliferation and the timely detection of diversion is on a scale of months to years, because inspectors are not going in every day to do these measurements. So if proliferation time was like an hour or 2 hours, I mean, we'd be lost. There's just no way to be tracking activities at facilities at that kind of, at that level. So does that make sense? There's sort of two different time issues we're talking about here. There's the time between inspections, which is months to years, and you want to hit those inspections before a weapon is developed. And then there's the time it takes to perform NDA measurements, which needs to be short in order to not inconvenience a nuclear facility so that they let us come in and do inspections. This is all an agreement. It's a voluntary agreement that states have signed up for. And if it turns out that them forming these safeguards contracts with the IAEA, if them agreeing to that completely causes them to have to like shut down and lose money and it's a huge inconvenience for them, they're not going to want to do it anymore. And that's hugely problematic. So, two different issues at play.
Yeah, thanks for that explanation. That really cleared it up.
Sure.
The last question that I have, which maybe is 24 hours too early, is so I'm hearing that you're going to talk about non-destructiveness, say, of spent fuel. But a question that just kind of pops in my head is, if it's spent fuel and maybe we're not planning on using it again, why wouldn't we just do destructiveness, say?
Good question, and it's just because there's so much of it. And it's, so power reactor fuel is, 4 meters long, it weighs thousands of pounds, and it's emitting, 10 to the 8th neutrons per second. So it's highly radioactive. It's a ton of material, literally. And so, melting down every assembly and measuring all pieces of every assembly would just take so much time and effort. And it would be so expensive. Reprocessing, a lot of places don't pursue it just because it's expensive. And this is really what we're talking about. You'd have to, start the reprocessing process to melt down all this fuel and measure it. So that's the reason we don't melt the whole fuel. You could theoretically chip off a little piece of material of spent fuel and go measure it. There are problems with that, which is that, the fuel is obviously clad and it's intended to not break. It's intended to not leak. And a lot of work went into sealing these assemblies so that no nuclear material could come out. So it would take a lot of effort, correspondingly to get into these fuel pins and remove some material. And then you'd have to seal it back up to put it back down in storage. So just logistically, really, it would just be really, really challenging. Like non-destructive assay measurements on spent fuel are already logistically really challenging, but destructive assay would just be, so much more logistical hassle, and therefore so much more expense that it's just really not plausible in a lot of cases. me being a spent fuel person, you know, I'm so interested in the content of spent fuel and the isotopic composition. I would love for them to melt down a bunch of spent fuel assemblies after I was able to come measure them so that we could have perfect calibration standards. But unfortunately, yeah, it's just such a difficult process that it's really not done very often.
Got it. Thank you.
Mm-hmm.
So it looks like chat questions have also slowed down.
All right.
So what I'll do is go ahead and stop the recording, and then I look forward to seeing everybody, and especially Alexis, tomorrow.
Sounds good. Thank you.
All right. Thanks, everyone.